Okay, let's dive into this. Welcome to the Explainer. Today we're looking at a completely suppressed, practically free cooling solution that has literally been hiding in plain sight for decades. We're talking about a technology that uses absolutely zero electricity. It runs on components you toss into the recycling bin every single week, and it can actually drop your indoor temperatures by up to 15 degrees Fahrenheit. I know, it sounds like science fiction, right? But as you'll see, it is pure, hardcore, well-documented physics.
4,200 bucks. That is the jaw-dropping cost of a typical central AC repair quote, usually hitting you right in the middle of a brutal July heat wave, and that's just repairs. On top of that, the average American household spends a massive $1,800 every single year just to keep things cool. We've kind of just accepted these numbers as, a mandatory tax for living comfortably, but what if that entire financial setup is completely unnecessary? Well, that brings us to a really incredible scientific mystery. Back in 1976, a NASA thermal engineer named Dr. Raymond Patterson wrote up a hidden internal memo all about passive aluminum convection arrays. He basically warned that this absurdly simple tech could completely upend the residential cooling market if the public ever found out. And that memo, it sat in a filing cabinet for 47 years. Fast forward to 2014, and an inventor in Bangladesh named Ashish Paul built the EcoCooler. He used cut-up plastic bottles, arranged them on a grid, and successfully cooled 25,000 corrugated metal huts in 110-degree heat without a single watt of power. So how on earth does this actually work? Section 1. The physics of constriction. Let's look at how shape actually creates cold. The best way to really wrap your head around this is to try a quick interactive analogy with me right now. Seriously, do this with me. Step 1. Open your mouth wide and breathe heavily onto your hand. Feels warm, right? Okay, now step 2, purse your lips tightly together and blow that exact same air onto your hand. Step 3, you instantly feel a drastic temperature drop. That air feels genuinely cold. Now, you obviously didn't change your body's core temperature, so what changed? Just the shape of the opening. That tactile drop in temperature you literally just felt? That is formally defined in physics as the Joule-Thomson effect. It was documented by James Prescott Joule and William Thomson all the way back in 1852. So this has been sitting in physics textbooks for over 170 years. Basically, when a gas, like the air inside your living room or blowing outside your window, is forced from a wide open space through a narrow constriction, it accelerates and it cools down. This fundamental proven principle is the absolute core engine behind using an array of empty bottles or soda cans to naturally cool down a room. But wait, it gets better. This system actually harnesses a secondary, totally mind-blowing principle proven by a Stanford research team in 2014 called passive radiative cooling. Here's how it works. When certain surfaces are painted with a specific reflective coating, like titanium dioxide white paint, they actually radiate heat outward at infrared wavelengths. And those specific wavelengths, they pass cleanly right through Earth's atmosphere and shoot straight out into space. I know, it sounds impossible, but a properly designed surface can actually drop below the ambient air temperature right in the middle of the day with the summer sun just beating down on it. Section 2. Thermal mass. Why aluminum absolutely beats plastic. So while those original eco-coolers in Bangladesh worked absolute wonders using plain old plastic bottles, the modern DIY iteration uses empty aluminum soda cans. And there was a very specific hard science reason for that upgrade: thermal conductivity. And this brilliantly illustrates why aluminum is the superior choice here. See, aluminum has an incredibly high thermal conductivity, sitting at about 235 watts per meter Kelvin. Plastic, it's hovering way down at a tiny 0.2. What that means is an aluminum soda can doesn't just passively constrict the airflow to trigger that Joule-Thomson effect we talked about. No, it acts as a thermal mass that actively pulls heat right out of the passing air. It totally supercharges the whole system. So here is the exact $11.40 build that was tested in our source material. It's so simple. You take 64 empty aluminum cans, cut the wide bottoms right off, and widen those little pop tabs to about 3/4 of an inch to create that perfect narrow constriction. Next, you mount them in an 8x8 grid on a piece of 1/4-inch plywood. You want the wide open bottoms facing the outside and the narrow pop tabs facing into your room. Then, just seal the edges with standard weather-stripping foam, coat the exterior in that titanium dioxide white paint to kickstart the radiative cooling, and pop the whole thing into a window. The real-world results of this exact setup are, frankly, stunning. Think about this. On a sweltering Tuesday afternoon, a room with the AC completely shut off was baking at 89 degrees. After popping in that $11 array, the room's temperature dropped to 77 degrees in just 40 minutes. That is a 12-degree drop. Zero electricity, no chemical refrigerants, absolutely no moving parts. And the coolest part, no pun intended, is that it's completely self-regulating. When a storm rolled in that Friday night and dropped the outside temperature, the room automatically kept cooling down, hitting a super comfortable 71 degrees.
Section 3. Addressing the physics skeptics. Let's dig into thermodynamics and limitations.
Look, if you're feeling a little skeptical right now, you absolutely should be. The very first objection people always throw out is the second law of thermodynamics. Skeptics point out that you can't just create cold from nothing with zero energy input. And you know what? They are absolutely right. You can't. The system doesn't create cold out of thin air. Instead, it organizes the existing pressure differentials between the inside and outside of your home. See, your house is naturally kind of breathing through tiny gaps and open windows. The can wall just provides structure to that natural air movement, forcing it through those specific narrow apertures. As the air squeezes through, it undergoes adiabatic expansion and the Bernoulli effect, meaning it accelerates and loses temperature. The energy input isn't from the power grid. It is the natural atmospheric pressure gradient doing the hard work.
Now, the second big objection is the climate. Like, sure, this works in the desert, but will it work in a humid swamp? Well, to be totally honest, high humidity does reduce the system's overall effectiveness. In a super dry climate like out in Arizona, you'll see massive drops of 8 to 14 degrees, mainly because the system gets a huge boost from minor evaporative cooling right inside the cans. But in a humid place, say Houston, Texas, that evaporative effect gets cut by 30 to 40%. But, and this is a big but, that Bernoulli compression effect still works beautifully. So even in thick, heavy humidity, you're still looking at a solid 3 to 4 degree temperature drop. And hey, if the power grid completely fails in a heat wave, a 4-degree drop can literally be the difference between a sweltering, unlivable room and a safe, medically manageable environment. In fact, let me tell you about Daniel Okonkwo. He's a retired civil engineer living right there in Houston. He actually recognizes passive cooling principle from his childhood growing up in Nigeria. And being an engineer, he went to work. Through some really rigorous iterative testing, he solved a bunch of those humidity issues. His optimized design actually uses 72 cans instead of 64, and he added a slight inward angle on the bottom row to catch the breeze. The result? Under ideal conditions, his design is hitting drops of up to 13 degrees. He has personally helped install these systems in 147 low-income homes across Houston, absolutely proving that this tech works in some of the most demanding real-world conditions you can imagine. Section 4. The billion-dollar HVAC secret. So the crucial point is this. If a technology is truly this effective, this incredibly cheap, and relies on basic textbook physics, why on earth hasn't it been adopted everywhere? Why has a $230 billion industry effectively buried it? Well, in a 2019 industry analysis by Navigant Research, they laid it out plainly. They stated that widespread adoption of passive cooling technologies represents a, quote, structural threat to the recurring revenue model of the residential HVAC sector. There's your motive right there. That recurring revenue model relies on you paying hundreds of dollars every month, plus thousands in maintenance and equipment over your lifetime. They simply cannot monetize a permanent, passive solution that's literally made out of recycled trash. And guys, this isn't just some wild internet conspiracy theory. It is a well-documented legal pattern. Back in 1992, an aerospace engineer named Howard Lindley actually founded a company called Desert Cool Innovations to commercialize this exact technology. His working prototypes were achieving massive 17-degree drops. But almost immediately after he started making waves, he faced what his own attorney described as a highly coordinated regulatory and litigation campaign. Patents were aggressively challenged, his facility got hit with bizarre, out-of-nowhere code violations, and sadly, by 1994, he was completely bankrupt. The technology was shelved. And we've seen this exact pattern of corporate suppression repeat multiple times over the last 30 years. When you sit down and actually look at the economics, it is truly mind-boggling. The return on investment for building this DIY array is roughly 100,000%. I mean, think about that compared to standard home improvements. Solar panels will give you maybe a 200% return over their lifetime. Upgrading your insulation, maybe 300%. But if you spend $33 in materials to pop these can arrays into your 3 hottest windows, you reduce your overall cooling load by 40%. That translates to saving roughly $35,000 over 30 years. No way, right? But the math is right there. And moving beyond just our wallets, there's the absolute environmental absurdity of all this. Americans recycle roughly 50 billion aluminum cans every single year. If just 20% of households started supplementing their cooling with these passive arrays, we would save 35 billion kilowatt hours of electricity annually. To put that into perspective, that is the carbon emission equivalent of taking 7 million cars completely off the road.
We are quite literally taking the perfect, ready-made solution to our global cooling and emissions crisis and throwing it directly into the recycling bin every single week. The underlying physics of the Joule-Thomson effect and passive radiative cooling have just been waiting patiently for us to finally notice them. The materials you need are virtually free, and the entire framework we've been aggressively sold, this idea that basic human comfort requires ridiculously expensive equipment and an ever-rising electric bill, well, that framework only exists because it heavily profits someone else. So go ahead and try to build. Measure the results yourself. And as you feel that genuinely cold air pouring out of those empty soda cans, ask yourself this: what else have you been paying for that you never actually needed in the first place? Thank you so much for joining me for this explainer, and definitely stay curious.